Sodium chloride, NaCl, has been known since ancient times to form crystals with the shape of a perfect cube. In the 19th century, the density of crystalline NaCl was measured and found to be 2.165 grams per cubic centimeter. In the 20th century, we learned how to scatter X-rays from an NaCl crystal in order to determine the size of the crystallographic unit cell. Using the information provided above and any crystallographic data available to you in the International Tables for Crystallography, determine the following. 1. The crystallographic unit cell, aka the Breavais lattice, of sodium chloride. 2. The lattice constant of the sodium chloride unit cell. 3. The number of sodium chloride molecules in the unit cell. 4. The locations, expressed as fractions of a unit cell constant, of all sodium and chlorine ions in the unit cell. That was an exam question for a first-year crystallography student. I'm sure that to the vast majority of you it barely sounded like English, but I promise, stick around, and by the end of this video, not only will you have the tools to fully answer that question, but we'll actually go over how useful crystallography has been to the development of modern society, as well as how it continues to advance cutting-edge technology in various fields. To make sure everyone's on the same page, let's go ahead and define some of the terms that we're going to be using throughout this video. The four main building blocks of crystallography, at least for our purposes, are the basis, the lattice, symmetry operations / space groups, and the unit cell. First of all, the basis. This is the actual material of the crystal. For diamond, it'd be the carbon. For salt, it's the sodium chloride molecule. Technically, anything can form the basis of a crystal, but for our purposes, I'll be using atoms, so we'll be using atoms and basis pretty much interchangeably. They'll be represented by these foam balls. The red and blue sides are going to be the handedness of the atom, which will become important when we're dealing with symmetry operations. The lattice is a purely mathematical construct. It's not like there's an actual physical object floating in space around the basis material, turning it into a crystal. Rather, the lattice is a representation of the math crystallographers use to define crystals and work with them. It's less a physical part of the crystal and more the graph paper you use to line things up properly. As such, I'll be representing lattice points with dots on the actual graph paper. Now, notice how I made them all evenly spaced apart? That's because of a property called translational symmetry, the first of our symmetry operations. Symmetry operations are transformations that we use to decorate the lattice to describe where the crystal's atoms can go, while still maintaining a regular crystal. These are also known as space groups when we're dealing with collections of symmetry operations in an actual crystal. Translational symmetry means that if we take the position of existing lattice points and shift them to other valid locations that are also on lattice points, then we will get as if nothing had actually moved, thus preserving translational symmetry. Or, in other words, we need to preserve translational symmetry, and to show that translational symmetry has been preserved, we must make sure that all lattice points have the same environment. Actually take a moment to let that sink in, because that will be foundational to pretty much everything else we talk about in this video. This is essentially the fundamental theorem of calculus, but for crystallography. Okay, everyone had a moment to absorb that all lattice points must have the same environment in order to preserve translational symmetry? Good. Then let's show the other symmetry operations that we'll be working with. At the simplest level, there are three possible symmetry operations. We've already seen translational symmetry, where you just move an object along a line. That is essentially going to become our fact-checking later on to make sure that nothing else has invalidated the regular lattice. The second symmetry operation is rotational symmetry. Rotational symmetry is how many times an object will be repeated when we trace out one full rotation around the rotation axis. So if I take this twofold here, then we have the initial lattice point, and that gets repeated one other time at a 180-degree rotation, then another 180 degrees, and it gets back to the original. So there are two total objects, hence twofold. If we had, say, a fourfold here, then we can't do that in 1D because it would require getting lattice points down here and up here. But it would, if we could, take this one, rotate it 90, 180, 270, 360, and as a result create a total of 4 lattice points around it. Hence, fourfold. Oh, and by the way, these tokens are actually following industry standard. So if you look in any kind of crystallographic text that deals with symmetry operations, then you will see ovals for 2 folds, triangles for 3 folds, squares for 4 folds, and hexagons for 6. Anyway, the final of our basic symmetry operations is the mirror plane. This works the way you'd probably expect a mirror to. Takes an object, then teleports it to the other side an equal distance away from the mirror, and then flips the handedness of that object. So left hand, right hand. For our purposes, I'm going to be starting all atoms on the blue side, and then any with reversed handedness will go to the red side. So now that we know about the lattice, basis structures, and symmetry operations, that means that we can finally form unit cells. A unit cell is the area of a crystal that we choose to act as one tile. Once we've determined what that tile is, we can repeat it infinitely in any direction and get a perfect crystal. And that's an emergent property due to all lattice points having the same environment. So if we tile them out in any direction, we'll get the same unit cell repeating over and over and over again. So, now that we have the basics in place, let's have some fun and build some actual unit cells. Eventually we'll work our way up to 3D unit cells to answer that question from the beginning, but as with many disciplines, knocking the problem down a few dimensions can help with building an understanding of how things work. So, let's start with a single dimension. A 1D crystal lattice is just a line of lattice points like what we made before. As a reminder, these points are evenly spaced in order to preserve translational symmetry to make a regular crystal. All lattice points must have the same environment. First of all, we need to know how the various symmetry operations are going to affect the crystal, so let's just place an atom. Congratulations, you just made your first crystal. Obviously things can get more complicated from here though, so let's throw in some actual symmetry operations. First of all, let's try out rotational symmetry. So let's put a twofold on the lattice point, and that swings the atom 180 degrees to the other side. And then of course that happens at all other lattice points. And to simplify, let's just consider these two for a moment. So, is this a valid operation? Well, it looks like it to me. The two lattice points appear to have the exact same environment, and if we just start this last point here, then it'll replicate just fine. Yeah, that's a totally valid arrangement. So, what happens if we replace the rotation with a mirror plane? Well, first things first, mirror plane on the next lattice point too, because same environment. And since it's a mirror, it'll go to the other side in reversed handedness. And same environment means blue on left. And that doesn't look like it violates anything, so we should be good to go. But both of those operations are with the symmetry operations being on the lattice point. What if it's not? If we instead place the mirror plane just a little to the side here, we can actually tell without even placing anything that this won't work, because this lattice point will reflect over to here, and that means that the distance between this lattice point and the hypothetical one this lattice point and the previous lattice point, and the hypothetical lattice point and the next lattice point are all different distances. And so they do not have the same environment, and so will not make a regular crystal. Does this mean that the lattice point is the only place we can put a symmetry operation then? No, actually. If we place it exactly halfway between two lattice points, then put an atom here, let the mirror act. Same environment means put this one over here. And likewise, same environment, put this one over here. That's totally valid, and the lattice points clearly have the same environment. In fact, not only do they have the same environment, we can do more. We can actually put a mirror plane here on the lattice point, and another one here on the other lattice point. Because the reverse-handedness atom and the regular atom are equidistant to the lattice point, and of course have opposite-handedness. And then the same on this side. And yeah, these emergent symmetry operations that seem to just pop up out of nowhere due to how the atoms are placed, that is very common when building unit cells like this. Because of the increased number of symmetry operations in this example as opposed to the previous one, we refer to this new unit cell as having something called higher symmetry. Back on topic though, that's pretty much as complex as we can get in 1D, so let's get into 2D crystals. The good news is that the method for how to construct a 2D lattice is very simple. You just take a bunch of 1D lattices and you stack them on top of each other. The bad news is that we don't actually have enough information there. We don't know if, say, the distance between this point and this point is going to be the same as the distance between this point and this point. They could be different distances, different lattice vector lengths. Likewise, we don't know if these points line up at 90 degrees here. They could be shifted over. There's nothing stopping that. So, how do we begin to figure this out? Well, the answer is actually extremely simple and surprisingly elegant. We just permute the options. To start with, we label this distance, or this vector, as A. And we label this vector as B, and the angle between them, gamma. And we know from the fact that we're just stacking 1D lattices here that we're going to be making a 4-sided polygon no matter what the arrangement is here. So, that means that we have 4 total options here. We have A equals B, gamma does not equal 90, A equals B, gamma does equal 90, A does not equal B, gamma equals 90, and A does not equal B, gamma does not equal 90. And since we're dealing with 4-sided shapes here, this should be raising some bells for some of you, because a 4-sided polygon, A equals B, so all sides are the same length, gamma equals 90, so all internal angles are 90, that's just a square. And since that's just a square, A does not equal B, gamma equals 90, that's just a square with a truncated pair of sides, also known as a rectangle. And so, A equals B, gamma does not equal 90 is basically going to be a square sheared to the side, also known as a rhombus. And that leaves A does not equal B, gamma does not equal 90 as the most general case, that being a parallelogram. And that actually gets us our 4 possible lattice shapes in 2D, technically called space lattices. However, there's actually one more to account for. Rectangular space lattices can actually have a centered construction as opposed to primitive space lattices where all of the lattice points are in the corners. In order to get the centered lattice unit cell, we stack 1D lattice point rows in another way. Since gamma equals 90, we can essentially line up every other row of lattice points, and then the ones that are not lined up, we can then shift half of a unit cell. So this isn't going to be exact, but it's going to be something like, and then these go around center. So this then creates a new A that is that long, B that is that long, and gamma, which is 90, while also still having a lattice point in the center. And again, since we shifted this half of a unit cell translation to get it to the center, what we're doing here is essentially that, translate by half to get about to there, then translate by half again to get to about there. A little bit misaligned due to user error, but don't worry. And as such, we can actually see that we're preserving translational symmetry when we do this, since we're just translating by half a unit cell, and everything still lines up to create one of those 4 polygons. And those 5 options are the space lattices of 2D crystallography, meaning that every unit cell must have one of those 5 shapes in 2D space. The remaining complexity comes from adding in symmetry operations, so let's add some and see what happens. To start with though, let's finally actually define rotation axes a little better, because with 1D crystals our only option was a 2-fold axis, but now we have a new dimension to work with and so it can rotate a little more freely. However, it's not like we can just rotate however much we want. The atoms can rotate and not change, but the lattice points must maintain their translational symmetry, and that restricts what rotations we can use. Specifically, we can actually end up using 0, 60, 90, 120, 180, and 360 degrees, corresponding to a 1, 1, 2, 3, 4, and 6-fold axis respectively. But let's actually prove that. Okay, so to start with, let's just make some lattice points, different color now to differentiate them from the ones that came before. Now, of course, we can just literally use a protractor here or count out the number of squares in order to figure out what the distance is. But let's assume that we couldn't just do that and can't just see that it's a 90-degree angle. What we want to do is put a rotation axis on this point and this point in order to swing this point up to here and this point over to here. However, since we don't know how much we can rotate, we need to use trigonometry, because we can consider this as a triangle with some angle theta, and this as the same. And hey, what do you know? These 2 center areas are the exact same distance. So that means that whatever this distance is just the same distance plus 2 cosine theta. And here's where translational symmetry gets really cool. Because if we assume that all these are lattice points or some other thing that requires us to preserve translational symmetry, that means that the distance between 2 lattice points must be the same in all rows of lattice points. So, if we're rotating from a lattice point up to another lattice point, that means that A here must be some multiple of the distance between lattice points, and so must A plus 2 cosine theta, because we end on 2 lattice points. So for the sake of ease here, we're going to be assuming that it's just one point to another, so A is the distance. But it could be more, it would just complicate the math more. As is, we have A equals... Whoops. Almost messed that up, sorry. We have A plus 2 cosine theta equals some integer multiple of A, because we both start and end on lattice points and are going to other lattice points. So it has to be some multiple distance of the distance between lattice points, and it has to be an integer in order to land on the lattice points. So, divide by A, 2 cosine theta equals some integer. And yes, technically that should be 1 plus 2 cosine theta. You can just do minus 1 there in order to get n minus 1. It doesn't actually matter. The point is that over on this side is an integer of some value. Because here's the thing. Cosine, by default, can only output between -1 and 1. So, 2 times cosine theta is only going to equal an integer at 5 or 6 values. 0 degrees, 60, 90, 120, 180, and 360 degrees if you want to go all the way back around. As a result, we are stuck with specifically 1, 2, 3, 4, and 6-fold rotation axes, because those are the only valid rotations given this. Okay, so we're going to start with something fairly friendly and just assume a square lattice. A equals B, gamma equals 90. By the way, now that we're moving into 2D lattices, I'm going to be representing lattice points with these foam balls, rather than actually drawing in each individual lattice point. So, where do we actually start with all of this? Well, we know that the unit cell is going to be shaped like a square, A equals B. So, you might have some intuition that we should use a 4-fold rotation, the square one here. Can we actually reason why that is, though? Well, with a 4-fold, everything gets rotated 90 degrees per rotation, so that would swing a lattice point in line with the rotation axis up to directly above the axis. Given that we know A equals B in a square, the lattice point staying the same distance from the rotation axis then means that it swings from, say, this location to exactly this location, and thus it will preserve translational symmetry, and so is valid. So, let's go ahead and put a 4-fold axis on the lattice point, and then of course all the other lattice points get 4-folds as well. Okay, so now that we have some 4-folds in place, let's go ahead and place some general location coordinates and see what happens. Well, the good news is that the 4-fold works just fine. The bad news is that 3 of the 4 atoms are outside the unit cell. How do we take care of this? Easy, we don't. No, seriously, there's nothing actually wrong here. Everything's working perfectly fine. Keep in mind that the unit cell is tileable. There's another perfect copy of the unit cell on every other side of this one. So, all these other atoms aren't actually outside of the unit cell, they're swung into neighboring unit cells. Additionally, that actually means the other 4 folds around here are doing the exact same thing, so let's go and place the atoms around them too. And that gets us 4 total atoms inside of the unit cell, and another 12 that are rotated outside of it and into neighboring unit cells. So, is that it? Are we done? Do we have a valid unit cell here? Not quite. Due to how the atoms are placed, we actually know that each of these is exactly a 90-degree rotation away from the others. As such, we can actually place a fourfold here, directly in the middle of the unit cell. That will cause the lattice points to rotate 90 degrees, which is totally okay, and that'll cause the atoms to rotate 90 degrees, which is totally okay. Also, as a little bit of a sneakier thing, notice how we have, say, this atom here, directly 180 degrees rotated from this one, across the point in the exact middle of this lattice vector. That is a hallmark of being able to place a twofold rotation. And of course, then the same logic holds for here to here, 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 and if you want to re-verify it, here to here. So that means two folds on this, and this lattice vector as well. Congratulations, you have just created the P4 unit cell. Named for being a primitive unit cell, so there are only lattice points in the corners here, based on just the fourfold rotational axis and nothing else. Next, let's get some practice with some higher symmetry unit cells before moving into 3D. First though, let's step back for just a moment in order to expand our toolset a little bit, just so that everything in the following example makes sense. We've already learned about the basic symmetry operations, translation, rotation, and mirrors. However, 2D unit cells actually give us access to our first combination of those three into a new operation. The glide plane. Glides are the combination of mirrors and translation. So it's like moving the atom along the glide for some distance, then jumping it across as if it were a mirror. Then you just repeat the process again, and it jumps across again. However, we still need to preserve translational symmetry, so we're restricted on where we can have the atom use the mirror part of that glide plane. We know that if we don't translate the atom at all, we just leave it where it is, it'll mirror across, no problem. We also know that if we translate it exactly one unit cell, then mirror it across, also no problem, because that's the same as if we hadn't moved it at all, and so translational symmetry is preserved. Where else can we go, though? Well, as with most things in crystallography, the answer is, technically anywhere is valid, as long as the lattice points maintain their translational symmetry. This ends up meaning that a glide plane is only able to act in one way, by translating the atom half of a unit cell length and then mirroring it across. If the glide oscillated any more frequently or any less frequently, then it would break translational symmetry due to multiple atoms being misaligned with the lattice points, effectively changing their position per unit cell and breaking translational symmetry. Now, as a slight technicality here, the actual answer to where a glide plane can drop the atom is actually 1 over 2 to the n, because that would still create a valid lattice due to lining up with the next lattice point after however many oscillations. However, if the glide acts multiple times within a single unit cell, then we can just rescale the lattice down so that it matches 2 oscillations of the glide plane, and that doesn't harm anything, and so it makes it so that the glide plane returns to oscillating once per unit cell. Okay, so now that we know what glides are and how they work, let's go with our last example in 2D and make a rectangle. So, as a quick reminder, this is A does not equal B, gamma equals 90, and because of that, we actually know that each of these lattice points should have a twofold on it. After all, we can't swing it up the same way we did with the square because the lattice points won't line up properly, but we can rotate 180 degrees and that will line up properly. Now, instead of just starting with the base assumptions due to the structure of the crystal here, I am actually going to assume that the lattice vectors here are also mirror planes. Please note that this is not due to any kind of emergent property or anything. This is just playing with the unit cell and seeing what happens if we decide to change one part of it. So that means that if we decide to place an atom near the corner here, we will then, due to this mirror plane, get a reversed one here. Then, due to the tiling of the unit cells, we then get another reversed one here. And then, likewise, by the same logic, we get one up here. So that's just translated one unit cell length up. And then, due to this mirror plane, all of these get reflected over to this side. Which you can probably then figure out that due to translational symmetry, all lattice points must have the same environment, means all of these get put over here as well. And if you want to logic it through by using the mirror planes and the infinite tiling of the unit cell and everything, by all means, that gives you some extra verification that it does in fact work. Or you could just realize that red, blue, blue, red, that's one lattice point, copy, paste, copy, paste, copy, paste. So, now that we have all of these atoms placed, we can actually see that there are some emergent symmetry operations that will come out of this. First of all, if we look at this atom and this atom, we can see that they are equal distant from the center of the unit cell and reversed handedness. Likewise with these and these and these. Basically, that means that there is now a new mirror plane here. And you can use that same logic for here to here, here to here, here to here, here to here, so that means there is a vertical mirror plane here. And then along with the mirror planes, we can also see that same handedness rotated 180 degrees around the lattice vector. Verified there. Same with this, and this, and this. So that means like with P4, two folds go in the center of each of the lattice vectors. And that is a completed unit cell. Specifically, it is P2MM, if you're curious. But we're not done quite yet. Remember what I mentioned back when I was first introducing what shapes the unit cell could take? Rectangular unit cells have another form in 2D space. Instead of just having the primitive form, like the others, where the unit cell's lattice points are in the corners, the rectangle also has a centered form, where there's an additional lattice point in the center of the unit cell. Of course, all lattice points must have the same environment, so just because it's in the middle of the unit cell doesn't change that fact. So, we need to add a twofold to the middle. Luckily, the mirror planes that we generated before match the mirror planes that all the other lattice points already have. So we're good on that front. As for the atoms, we can already see that we're going to be making some mini rectangles, but what handedness do we use? Well, since all lattice points have the same environment, let's just look at the other lattice points and kind of copy-paste them over to the middle one. So that'd be red here. Being a little tight on space, unfortunately. Blue here. Blue here. And red here. Well, that works, but now it's pretty clear that we're not done quite yet. Most obviously, each quadrant of the unit cell now has two atoms that are rotated 180 degrees from each other about the middle of the quadrant, equal distant from the corner and the center. So, since they're the same handedness, rotated 180 degrees from each other, let's go ahead and add in 4 twofolds. The other remaining issue is a bit more difficult to spot. Focus for a moment on the upper left corner here. From here, half a unit cell down and closer to center is one of the blue atoms, so reversed handedness from the starting red atom. Then another half down and back over is another red atom 1 unit cell length away. That is a textbook example of a glide plane at work. So let's pick these up and put a glide plane first. And as you might have already intuited, anything that happens on this side is also going to happen on this side. So, does it work? Half down and across, half down and across. Yup. And as with the mirror planes, everything we just did vertically, we can also do horizontally, although it's gonna start getting pretty tight in here. Just as a quick check, half a unit cell and across is blue from red, half a unit cell and across is red. Yep, glide plane there. On the other side, half unit cell up, yep, half unit cell down, yep. And then same with the other side. And replace the two folds. And that is everything done. If you're curious, this unit cell is actually called C2GM. So in other words, a centered unit cell based on a two-fold rotation axis, glide plane, and mirror plane. And that's actually going to be our last 2D demonstration, since anything more complicated, we're just not going to have room for at that point. In total, there are 17 possible 2D unit cells. If you want a bit more practice, then by all means, go ahead and look them up. We are going to jump now, though, into 3D and start getting into some real-world experiments and applications of crystallography. Okay, so now that we're going into 3D space, let's take a beat and regroup ourselves to make sure we're still on track for our goal. We're trying to figure out the unit cell of sodium chloride. To do that, we're going to need to figure out a few things. First of all, what are the possible space lattices, especially with any non-primitive options? We had 5 in 2D, but how many do we have in 3D? Next, how many molecules of sodium chloride are in a single unit cell? Finally, what is the crystal's space group? In 2D, we only had 17 in total to work with, but in 3D, we have 230. Now, the good news is that there are only 230. In other words, we know that somewhere in here is the answer. We just need to figure out which one. So, to start going into 3D unit cells, how do we actually start? Well, the same logic that got us from 1D to 2D actually still works. We just stack the previous dimension's lattices, ensuring that translational symmetry remains intact. Unfortunately, in 2D, we figured out the space lattices by just permuting the different shapes based on vector length and angle. That doesn't work in 3D. So, let's start with the good side of the equation and see where that gets us. If we just try to stack 2D lattices, what can we learn? Well, at the simplest level, we can just put one lattice on top of another some distance away. Since each vector of the lattice can be a different length, that makes a perfectly valid 3D lattice. So, congrats! That is the primitive orthorhombic space lattice. What else can we do? Well, we were working with C2MG before, so can we stack a centered crystal structure? Absolutely. In fact, there's no reason we can't just do the same thing as before, just with a centered lattice. This one is the base-centered orthorhombic system. Base-centered is referring to how only one pair of faces is centered. The remaining 4 faces are all primitive. Let's extend out this logic then. When we first made the centered rectangle space lattice before, the reasoning was that we essentially skipped over a row of the lattice and offset that row by half a unit cell length. Can we do something similar here? Absolutely! In fact, it actually works the exact same way. Instead of lining up the 2D lattices directly on top of each other, we stagger them so that the ones on top and bottom are lined up, but the one in the middle has one of its corners in the center of the 3D crystal structure. This creates a body-centered orthorhombic structure where there's an extra lattice point in the exact center of the unit cell, much like with the centered rectangle for 2D crystals. And if you're very clever, you might have already realized that there's one more possibility. Until now, we've been talking about the height of the unit cell as a pretty much random value. But what if it matched the length of the 2D unit cell? Since the width already matches, that would make it an exact copy of the 2D version, just vertical instead of horizontal. Now, for reasons that are a bit too granular for this video, this only works with centered 2D lattices, but since the two lattice vectors are the same length and meet at 90 degrees, that means that the final pair of sides are actually squares. And in fact, they are centered squares. Unlike in 2D, simply rescaling the square would change the symmetry operations in 3D, so a centered square face is now a thing for us to consider. That is the final orthorhombic space lattice, the face-centered orthorhombic. This is where every face of the crystal has a lattice point at its center. Now, we could go over all the possibilities for how to make 3D space lattices, but all of them fall under those four categories of primitive, face-centered, base-centered, and body-centered, with one example of a rhombic crystal based on the 2D rhombus. But actually deriving all of them and proving that they're both possible and the only possible options is an extremely granular topic that honestly warrants its own video. So for our purposes, these are all of the possible lattice structures in 3D space, collectively known as the Breavais Lattices, named after the researcher who proved they are the only possible 3D lattices back in 1848. In total, we have 14 options, along with the 4 orthorhombic ones we just went over. We also have the isometrics, or cubics, tetragonals, monoclinics, triclinics, and finally the hexagonals. And they're split into the categories that I mentioned before: primitive, body-centered, face-centered, base-centered, and rhombic. And this is incredibly helpful for us. Each of the 14 Breavais lattices can only utilize a small number of the total number of space groups. So it's possible to organize all 230 options into just a total of 7 or 8 groups based on the overall shape of the lattice. And that'll tell us the remaining number of possible space groups. It doesn't actually narrow the number down, but it does make it much easier to parse. If we can just figure out the shape of our unit cell, then that narrows it down tremendously to just a handful of possible options at most. Okay, now we still need to figure out what the actual shape of the unit cell is before we can do much more with that. The bad news is that we've pushed our current methods about as far as they can go. The good news is that this is a very easy wall to push through, since all we need to do is look at the internal structure of the salt crystal in order to figure out basically everything we need to know. To do that, let me introduce you to X-ray diffraction. The way X-ray diffraction works is that we set up a material at the center of the testing area, and then we shoot a beam of X-rays at it, and then rotate that X-ray source around the material. We then measure when the beam comes through no problem versus getting diffracted by the material, and that gets us this chart. Now, to be clear, we aren't exactly measuring the X-rays getting blocked by the atoms here. We're technically seeing what happens when the atoms create an interference pattern with the light's wavelengths. But X-ray diffraction is an entire field of study unto itself, so I'm going to limit myself to just talking about the parts of it that are useful to us when talking about crystallography. Luckily for us, the thing we're mainly interested in right now is how many peaks there are, which ones are missing, and how they're grouped. The reason is something I consider almost a miracle of nature. Each of the 14 Breavais lattices has almost a fingerprint that emerges due to X-ray diffraction. Each general shape, hexagonal, orthorhombic, etc., will have some maximum number of peaks grouped in a specific way. And each specific type of crystal, primitive, base-centered, etc., will then remove some number of those peaks. Now, one of the things that I don't have enough time to cover here is that lower symmetry lattices tend to create a larger number of peaks to the point where there could be dozens, and it's all very computationally difficult to actually compute all of those graphs. So, due to the difficulty of actually calculating all of the charts for each of the lattices, we're going to use a little bit of crystallographic trickery here. Namely, single peaks like this, and a relatively low number of them, like 10 or less. That is a hallmark of a cubic structure. So given that we now know that we're dealing with a cubic structure of some kind, that leaves us with the primitive, body-centered, and face-centered cubic to consider. And luckily, like I said before, all 14 of the lattices have something of a fingerprint we can look at. This is the face-centered cubic, the primitive cubic, and the body-centered cubic. And if we try to match up our experimental data from our sodium chloride, we can see that voila, it matches most closely with the face-centered cubic. The primitive has too many peaks. The body-centered also has too many peaks, and also they're pushed more over to the higher angles. The face-centered matches up pretty much perfectly. So, let's go back to our 230 possible space groups. We can throw out all but the cubic. And within the cubic, we can throw out many of these. Because, like with the 2D crystals, where they were labeled with P for primitive and C for centered, the first letter of each space group is the lattice construction. P for primitive, F for face. We're looking for the face-centered cubic. And that gets us our 11 candidates. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Let's clean this up a little bit, though. And here we have our 11 final suspects. We're not quite there yet, but we're getting close. Now, before we move on, I actually want to take a moment to talk about how amazing that last discovery was. For this entire video, we've been building up these crystals based on logic and reasoning. All lattice points must have the same environment, creates a regular lattice that then leads us to translational symmetry. Preserving translational symmetry gives us a set of symmetry operations, and applying those symmetry operations to general location coordinates then tells us where all the other general location coordinates are, and thus where the material of the basis in the crystal goes. All of it is reasoned. But this chart is the first time we're actually seeing that this isn't just some mathematicians cooped up in their offices making some nanoscale mathematical constructs. It's real. The actual universe is constructing these crystals, as crystallographers had started predicting over 200 years ago, and which we've only been able to truly start verifying during the 20th century. Personally, to me, that's one of the coolest things in this entire video. But anyway, back to our main investigation, the unit cell of sodium chloride. The X-ray diffraction graph is good information, but we need to dig deeper. Obviously, there isn't just one face-centered cubic crystal in the world, so where can we get more information? Well, let's see how many salt molecules are actually in the unit cell and see what that tells us. And we're in luck again, because the actual method for doing that is almost comically straightforward. We just count backwards. Specifically, we start with 1 mole of salt, then work our way back to the mass of salt in the volume of one unit cell using density. For those of you who have forgotten what a mole is, it's a unit of measurement defined as about 6 times 10 to the 23 molecules. For salt, we can learn from experimentation or a quick Google search that the mass of 1 mole is 58.44 grams, and its density is 2.165 grams per cubic centimeter. So we have its density, mass, and number of molecules. All we need is the volume of the unit cell, and everything falls into place. Okay, let me reintroduce you to density, since we'll need you in a little bit. And introduce you for the first time to Bragg's law. And, well, this one doesn't actually really have a name, it's more just a property of the lattice, but we'll get to that in a little bit. So, first off, Bragg's law. N is just an integer. We'll get to that in more detail in a moment, but it's basically just going to be 1. Lambda is the wavelength of light that we're dealing with. 2 is a constant. D is the separation of planes within the crystal. Realistically, it's going to just be the thing we solve for to put it into this to get this other thing, so we'll deal with that in a moment. And sine theta has to do with the angle to the peak that we're looking at. So, if we bring back the sodium chloride chart here, now with its peaks actually labeled, we can see that each of them has 3 numbers, and that those are actually labeled as H, K, and L, which will help out with this equation. Now, the actual reasoning here is because these labels are technically their Miller indices, which is to do with their positions in reciprocal space. It's not going to be important for us to know, it's just in case you want to know more, that's where it's coming from. So, over in the second equation, since we already saw that D is this and H, K, and L are these, A, the final thing that we're going to be ultimately solving for here, is the lattice constant. That is, for all intents and purposes, the length of one side of the unit cell. Which, since we're dealing with a cube, means we can just cube A, and that'll get us the volume of one unit cell. Okay, so, with all our variables accounted for, let's go ahead and do some math to work our way towards the number of sodium chloride molecules in one unit cell. First up, N. N can be 2 or 3 in more complicated situations, but realistically most of the time it's just going to be 1. And we aren't going to be dealing with any of those more complicated situations, so we're just going to call it 1. Lambda is the wavelength of light that we're going to be using in the diffraction experiment. A pretty common source of that is going to have a wavelength of 1.54 angstrom, so let's just use that. 2 is going to remain as 2. D is what we're solving for. Sine theta. What is theta here? Well, the answer is actually somewhat arbitrary. We can pick any of these peaks, and as long as we're consistent from this equation into this equation, we'll get the right answer. So let's go with peak 400 here, just kind of to choose one. And yes, they're labeled as 400, 420, 200. They aren't read as 400, 420, 200, anything like that. So, the sine of peak 400. We can see that it's around 65 degrees, maybe a little bit higher. And we can see the exact number here. 400 is 66.37. But, as you can probably see, that is 2 theta. So, let's have it down to 33.15, let's say. A little bit low, but it's close enough. Okay, and that gets us our actual answer, so let's just work through the math here. Okay, and that gets us D to then plug into the second equation over here. Okay, so next we have this equation. So 1 over D squared equals H squared plus K squared plus L squared all over A squared. And D we just plug in from the previous formula, so that's 1.408 squared angstrom equals H, K, and L, we literally just take the label of the peak here, because H, K, and L are what form that number. So, since we're looking at peak 400, we then have 4 squared plus 0 squared plus 0 squared. So those go to 0, this goes to 16, all over A squared. 1.408 squared is about 1.982 equals 16 over a squared. So, over 1, because then everything over 1 then gets us 1.982 equals a squared over 16 times by 16. And that gets us 31.719 equals a squared square root. And that gets us a equals 5.632 angstrom. Okay, so we have a. Though for the sake of ease, since this is currently an angstrom, 1 angstrom is 1 times 10 to the negative 10 meters. Density over here is going to be in cubic centimeters, though, so we're going to turn this into 5.632 times 10 to the negative 8 centimeters equals one side of our unit cell. Okay, so now that we have A figured out, so to get a volume we can just cube that. Let's get back to the density formula and figure out the rest of this. This is basically going to be a two-step process. First we go through the density formula, then we bring all the mole stuff in to make sure we can go from grams to molecules in the unit cell. So, let's start with density. Density equals mass over volume times by volume equals mass equals density times volume. Mass equals 2.165 grams per cubic centimeter times 5.632 times 10 to the negative 8 centimeters cubed. And again, we're going to be putting more stuff into that in a moment, but for now, let's just take care of this. So that means that mass equals 2.165 times 1.786 times 10 to the minus 22, which then equals 3.868 times 10 to the minus 22. Now, let's bring the mole stuff back into this. So, we then need to times this by Avogadro's number, the number of molecules in a mole, in order to have these magnitudes cancel out and get us from grams to molecules. Then divide by 58.44 grams per mole in order to cancel out the grams. So, we have 3.868 times 10 to the minus 22 times 6.02 times 10 to the 23 all over 58.44, which leads to our final answer of 3.984. And because we're not using hyper-accurate measurements here and not being careful to preserve all accuracy between all mathematical steps, we can round it off a little bit. So that means that this is equal to 4. A total of 4 molecules of sodium chloride in each unit cell. And be careful there, that is for molecules, meaning that it is 8 total atoms, because it's 1 atom each of sodium and chlorine per sodium chloride. Okay, so we know how many molecules there are, how many atoms there are, and what the shape and structure of the lattice is, along with having, as a result, a short list of possible space groups. We're almost in the home stretch, but we need a little bit more information. So let's go back to 2D space for a moment and get one last smoking gun. Welcome back to our old friend P4. Specifically, welcome back to our representation of atoms within the crystal. Up until now, I've been using the terms atom, basis, and general location coordinate pretty much interchangeably. But now it's going to become a lot more vital to understand that last term in particular, what it means, and when it's no longer accurate. On the simplest level, a general location coordinate is any random valid location for an atom in the unit cell. You can place an atom at the coordinate, and all the symmetry operations will act on it to automatically create the valid locations for more atoms. As such, you can move the general location around, and all other general locations will move along with it. But what if your random placement ended up, say, here? Well, we could have the central fourfold act on it, but the rotation axis is right in the middle of the atom, so it just spins in place. And the lattice point fourfolds can act on it, but a 90-degree rotation from the center of the unit cell is just the center of a neighboring unit cell. So that's it. We just created a P4 unit cell with one atom in the middle instead of 4 in the unit cell and 16 all around. Yes, actually. Due to the placement we chose, all of the general location coordinates converged into one place, reducing the total number of possible atoms in the crystal. This is what we call a special location coordinate. Since we can't just pick the location arbitrarily, it only happens at specific locations within the crystal. And we get another additional piece of information from this. All of the general location coordinates in P4 have what is known as rank 4. Meanwhile, the special position we just made here is rank 1. Ranks here indicate the number of equivalent positions within the unit cell. Basically, it's the number of positions that get created when you place a single one down and then just let the symmetry operations work their magic and tell you where all the others go. For sodium chloride, we know that there are 4 molecules in the unit cell and 8 atoms in total, so we're looking for a space group with 2 rank 4 special location coordinates to accommodate that. So let's finally return to our shortlist of 11 remaining space groups, with the knowledge that we must have 2 rank 4 positions in order to accommodate the molecules and atoms, and let's look at the international tables for each of these. Okay, so let's go through these one at a time and disqualify them or qualify them as we can. Now, don't worry, we don't need to know anything here. We just care about the name, and that's it. However, if we look on the second page, this is where things get more interesting, because these are the different coordinates. These are general location coordinates, and each of these are special locations. The number over here is the rank of the position. So we need 2 instances of 4 down here. And what's technically happening then is that each of these sets of positions are then multiplied into these coordinates to get all of the actual locations for that position. We don't care about that right now though, so we have 8 and 8 here, so we don't care about the space group. Next, F bar 4, 3M, 4 and 4. Okay, that is possible. So we will put you over here. F4 sub 132. The sub 1 has to do with screw axes. It's another symmetry operation that happens in 3D space. We have 8 and 8. Don't care. F2, 3. 4 and 4. And then 4 and 4. Okay. Keep that on the short list for now. We'll revisit that soon. FD bar 3M. 8 and 8. Nope. F432. The ranks got a little bit cut off, so it's 4 and 4. So let's go ahead and keep that for now. FM bar 3M, 4 and 4, good to keep. FM bar 3 has 4 and 4, okay. FD bar 3C, 16 and 32, nope. FD bar 3, 8 and 8, nope. And finally, FM bar 3C, 8 and 8, nope. Okay, so that cuts down our shortlist from 11 total space groups to 5. Now, to get it down from 5 to 1, the first step to this is actually going to be something kind of unexpected here. Because we have 4 molecules and 8 atoms, we actually know that whatever space group we use needs to have 2 things: a 4-fold rotation axis and an inversion. And the inversions are denoted by these minus signs over here, and the bars over the numbers here. Now, unfortunately, we don't really have time to get into why these are required, though from my perspective, it kind of logically follows that if you have 4 molecules with 2 atoms each in a cube, having a 4-fold rotation axis be required for it to be a consistent regular lattice just kind of makes sense to me. So, F23 does not have a 4-fold, and you can tell that because there's no 4 in the simplified name or the fully written out name here, so you're gone. FM bar 3 does have an inversion, but does not have a 4-fold rotation. F bar 43M, 4-fold and inversion, you're good to stay for a moment. F432, you have a 4-fold, but not an inversion axis, so you are gone. And FM bar 3M, you would think is probably gone, but no. The full description of the name here is F4 over M bar 3 2 over M. And what all that means is that the 4-fold has a mirror plane that's perpendicular to it, the 2-fold also has a mirror plane that's perpendicular to it, and also there's an inverted 3-fold. And that occurs at every lattice point. 3D space gets complicated. But that means that we have 2 remaining candidates. So we're kind of at an impasse now. We have 2 space groups, both of whom are face-centered cubics. They have 2 rank 4 positions. Let's check that again to be sure. 4, 4, 4, 4. They both have 4-fold rotation axes and inversions. So, how'd we pick between these? Well, let's reintroduce X-ray diffraction into the equation. Luckily, due to some very deep math that we very much do not have time for, go look up the structure factor if you want, we actually have predicted X-ray diffraction peaks for every space group. So let's compare the expected peaks of FM bar 3M to F bar 43M to our experimental sodium chloride data. Well, let's start by just directly comparing the 2 charts to each other, actually, because they're labeled as the 2 different space groups, but how do they actually differ? Well, the differences are very clearly there, but they really don't draw attention to themselves. The 2 peaks here are about the same location, but reversed intensity, so almost nothing, then the maximum for the entire chart, and the maximum, and almost nothing. And that's repeated at around a quarter intensity over at about 70-75 theta. 2 theta, technically. And there's a couple of other small differences, but for me, it's this around 30 degrees is the big smoking gun for this. So, let's compare to sodium chloride. And we can tell almost immediately that the experimental data for sodium chloride lines up with the left one and not the right one. we finally have our space group for sodium chloride, and thus our unit cell. Sodium chloride has a unit cell that is a face-centered cubic with space group FM*3M. However, we aren't done quite yet. If we want full marks on our initial question here, then we have to keep going. We've already determined that the unit cell is a face-centered cubic. We've shown through both math and experimental data that the lattice constant is about 5.6 angstrom, and we then worked through more math to figure out that there were 4 molecules or 8 atoms in the unit cell. However, we still need to determine the exact location of each atom in the unit cell. Luckily for us, that's actually incredibly easy now that we have the international tables. I glanced over this before, but these 4 coordinates are actually applied to each of these groups of other coordinates. So, as just an example for the general location coordinates here, they each have a rank of 192, meaning there should be 192 locations listed, but there are only 48. It's not like it's continued on the next page or anything though. That's because those 48 positions are then each applied to these 4. 48 times 4 gets you 192. So, for our measly little rank 4 positions down here, they each have 1 coordinate listed, because each of those coordinates is then applied to each of these 4 positions. 4 locations total by 2 rank 4 positions gets us our final 8 coordinates. So, how do we actually do this? Like, what do we do to apply these coordinates to these? It is actually as simple as it can be. It is just addition. And our first group here is all zeros, so it is somehow even easier. Technically, we should be adding them together, but because it's all zeros, we can just use our coordinates from up here. So that is 0, 0, 0, 0, half, 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 0, half, and half, half, 0. Those are our first 4 coordinates. Done! Our other group here is a little more complicated, but only just. It has all halves, 1 half, 1 half, 1 half, as the coordinate that we're applying to each of those 4. Now, like I said, it's all addition, so it's not like it's difficult. However, there is one technicality to keep in mind. These are all fractional coordinates of the lattice. So 0 is your starting point, and it's all in fractions up until 1, which is not the edge of the unit cell, but rather the start of the next unit cell. So in other words, if any of this math equals or exceeds 1, then we set it back to 0 or whatever equivalent if it's above 1. So we have a half, half, half as our start, 0, 0, 0. So that's half, 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 then plus 0, 0, 0 goes to half, half, half. Okay, now we start to get slightly more complicated, because we have half, 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 plus 0, half, half, which then becomes 0 plus a half is a half, 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 1, half, half, 1, which in turn then becomes 1 half, 0, 0. Going to underline those so I can keep track of them. Then it's that same logic for the other 2. So we have half, 0, half, plus a half on each side goes to 1, half, 1, goes to 0, half, 0. And then finally, half, half, 0 goes to, apply half to all of them, 1, 1, half goes to 0, 0, half. And in total, that gets us our 8 final coordinates. And as a result, we have now fully and completely answered our initial question. We could stop right there, but as a bit of extra credit for anyone who realized from this video that they're genuinely interested in this topic, or at least a specific area that we spoke about, here are some of the more modern applications of crystallography. First up, let's complicate space groups. Previously, I said that 2D space has 17 space groups, or collection of symmetry operations, and 3D has 230. And that's true in the simple case. However, when we started playing around with superconductors, people got really interested in 3D magnetic fields, and as such an entire new field emerged to figure out the magnetic space groups of materials. This used all of the previous space groups and symmetry operations that we're familiar with, but it also included a new variable, lattice points being considered black, white, gray, or colorless based on spin. This shot the number of possible space groups up from 230 to over 1600. Another field utilizing some of what we learned here today is electronics. It turns out that if you alloy silicon and germanium together, the germanium actually changes the silicon's unit cell, which in turn allows electrons to pass through the crystal more easily, thus allowing for faster electronics. And finally, if you've ever taken a prescription drug, then crystallography was almost certainly involved at some step. In the modern day, chemists use crystallography on new chemicals to determine the location of their atoms in order to figure out their chemical properties before testing them on anything living. But all of that gets way too advanced for anything I'm actually prepared to go in depth on, so I'll just thank you for watching the video, hope that you enjoyed it and learned something new, and wish you a wonderful remainder of your day. Hope to see you in the next one. Bye.